Hello, everyone. So good morning, good afternoon, good evening, depending on where you are. And welcome to Wind Down Friday. Today, our guest is Victor Veliadis. Hi, Victor. How are you?
Good morning and good day, I guess, to everybody around the world. Doing great. Glad to be here.
Great. Thank you. Thanks a lot for coming on. So, Victor, you are you are the executive director and CTO of PowerAmerica, which is a USA Department of Energy wide bandgap power electronics manufacturing institute, and a professor of electrical and computer engineering at North Carolina State University. So starting in terms of university. So tell me your activities. So which subject are you teaching? How do you organize activities with your students? How do you set up activities with your students?
Yeah. So before we get to that, I spent 21 years in the semiconductor industry. So I was working in industry, and then an opportunity came with PowerAmerica, which is managed by North Carolina State University. So it was a great opportunity in the sense that helping commercialize silicon carbide and GaN power electronics can help with climate change. This energy efficient is, really a passion for me, close to my heart. I think anything that we can do today to give a better future to our children and grandchildren is a very important thing, and that was part of the decision why I left industry where I was before with Northrop Grumman specifically, and joined NC State. So I've been at NC State. It's going to be 6 years in about 2 weeks. So time flies, and for the majority of that time, I've been running PowerAmerica. PowerAmerica is a $146 million project, and we've invested in over 200 projects with universities and industry. So that's been occupying most of my time. With respect to teaching, I've done, I would say, very little of that because of the time constraints, and it's basically semiconductor physics, and of course, in particular, fabrication of wide bandgap semiconductor devices. As you know, these devices basically do follow silicon fabrication for the most part, but there are processes that are specific to these devices that don't exist in silicon. So I've been teaching about that, and it's a very hot field. So students find internships, and as soon as they graduate, they have multiple job offers. So it looks really good, for the students, and as universities, as professor, I think we all have a responsibility to train as many students as possible in order for this growth to happen. It is actually a barrier, right? There's going to be millions and millions of, actually billions of dollars that are being invested in Europe, the US, everywhere, Spain, with a goal of, semiconductor manufacturing and fabrication. And certainly we need to have the people that are trained to do that work. So my activities with students are focused in the more practical aspects. They're focused in that direction. And a large number of the projects that I selected to fund over the years had to do with supporting fabs, equipment, process integration, device design, and those things. And of course, then the next step was, of course, the modules, because that also has a lot of technology that needs to be developed in the circuit insertion.
So I mean, you have a PhD in engineering, correct? And after the studies in Greece, your diploma, you moved in USA. So tell me, so after this moving, what are the differences you noted between your original country? You come from Greece, and the current one, USA, United States. So do you return often in Greece? Something that is missing?
Yeah, so I went through the 5-year engineering program, which is a diploma similar to the programs I think they have in Germany. And after graduation, I wanted to do a master's degree, continuing my education. And the United States was the natural choice. It's got a lot of good universities. Of course, the language is English. That I was very familiar with. So I kind of took off thinking, okay, let me do a master's degree for 2 years, and then Upon completion of that, I really liked the project, my PhD advisor, and continued on to do a PhD. Then I thought to myself, let's do a postdoc for a year to get some experience. And then kind of time flew. I forgot to move back. It takes a lot of momentum to make the change. So I ended up staying here. One thing of interest is that I was never a financial immigrant. I actually, had a nice home in Greece. I had a home in Greece near the Mediterranean, near the water, and it's I love the water. I love the sea. I love the Greek islands. So coming to the United States, was a rather big change. But I gotta say, it's a country that has a lot of opportunity, and it's a country where hard work and creativity gets rewarded. I think there are other parts of the world, and maybe Greece in the 1990s when I left was not in that situation. But coming to America, really, you don't need to know anybody to move up, right? When I left Greece, in those days, if you needed a job, you needed to know somebody who knew somebody, and so on and so forth. So what I appreciate about the United States is the fact that it has a system that trains people to be creative, to think out of the box, to produce things. And that's why most of the major advancements in technology have started here in the United States. And, the fact that, you're rewarded for your hard work, and there's an opportunity, that's a great thing about the US. And I'm very appreciative for the opportunities that this country gave me. Of course, it would have been nice if I could live in the United States and take a short drive and be on a Greek island and enjoy the water and the scene, but that's not possible. So I try to make it back, in Greece every summer. For the longest time, there was a military service requirement that I hadn't fulfilled, so that made it travel to Greece prohibitive, right? But then at some point I went back and I joined the infantry and, spend the time. Well, it was time well spent, it was
You
good
did,
training, helps you
you did a
understand.
military service in Greece.
The military
Um,
service, that's correct. It's a draft, right? You're a
okay.
conscript, you have to go. Back in 1990, when I was supposed to join, it would have been 2 years. But by the time I get back, it was 1 year. Time had shortened. So yeah, I mean, I love the United States. Give me a lot of opportunity.
Yeah.
My kids are here, and I want to see the country grow and succeed. And of course, I have my ties to my original country where I go back quite often.
Yeah, I agree with you. In terms of Greece, maybe on the same page of Italy at that time. And yes, USA, you have a great opportunities. How many kids do you have, Victor?
So three kids, three kids. One is older. She's 24. She's working. The other one just finished college, 22, and my son is going to be entering. And as far as I can tell, he will be doing engineering. Of course, there's always a lot of room to change your mind down the road. But
Yeah,
yeah. So
yeah. So I mean, for your PhD, just curiosity. So tell me, so you wrote a manuscript, a thesis, I mean, at that time. So what was the topic of your PhD?
So at the time, I got a scholarship, and I went to Johns Hopkins University. Originally, I was supposed to be biomed, but then I shifted more into electrical engineering. I got more absorbed into that, and I was looking into optical semiconductors. So I started working on semiconductors device design. I was in a lab. There were a number of lasers that those were dye lasers, which you really get your hands dirty there with all the dyes and everything, and they were prone to failure. Solid state lasers are a lot more robust. But I did a lot of work with optics, and I was looking into quantum wells and trapping mechanisms, and the role of defects towards the optoelectronics. And then the first job that I had gotten, which eventually went from Bell Labs to Lucent, was looking at optical semiconductors. I was making semiconductor lasers that were tunable, so you could go to different wavelengths and feed optical fibers with signals. And they also had a modulator that would turn them on and off. So it was what is called an electroabsorption modulator type of laser. It was really great technology, but that came to a sharp end in 2002 when there was a big crisis and the Nasdaq here dropped in half. So at that point, I went to the military for a while, and then after I came back, I got a job, and the company was very interested in doing optical semiconductors, but they said, well, until we get some grants, until we get some money to do that type of work, why don't you go into the fab and work on silicon carbide? And I guess I kind of sealed my fate because I got very much interested in that, and I guess it was a great opportunity because back in 2000, in the early 2000s, silicon carbide was like the Wild West. You needed to do an ohmic contact, you needed to do an implantation, you needed to do an anneal, you needed to come up with all these technologies, make sure they're manufacturable in a silicon fab setting. So I did a lot of that work, and my office was really, 20 feet from the fab. So I was in and out all the time, and I remember those days in the fab, you find a lot of peace. Nobody bothers you. You do your work. I spent a lot of time on the SEM. I spent a lot of time on the optical microscope, doing a lot of characterization, doing a lot of process integration, and some of the earlier silicon carbide devices came out of that work. So it was pretty exciting. It was very exciting. It was a lot of fun. And obviously, if you do a good job, they're going to punish you by taking you out of the fab and making you write proposals and bring money and run groups. So that's kind of happened to me as well. And at some point, this large $146 million program from the Department of Energy came, and they needed somebody to run it. And that's how I shifted from the industrial work to the university setting.
Great. So you have several patents. So I mean, which is if there is a favorite one? So tell us just some examples where we are using those patents.
Yeah, so the work that I did in those days, in 2008, it was licensed. 2007, I think 2008 timeframe.
Mhm.
It was licensed to a company that was called Microsemi at the time, and they
Yeah.
took this technology, and I think a lot of it was used to, for their silicon carbide offerings. And you're very familiar, of course, Mauricio, with the vertical integration. And all the companies that want to enter silicon carbide, their first thought is, do I start from scratch and compete with companies that have been doing this for 20 years? How do I get a jump start to make it to market and be competitive? So Microsemi had a lot of that silicon carbide technology, and it was bought by Microchip. So in a way, I'd like to think that some of the work that I've done has found itself in the commercial sector down the road in some shape and form. Of course, there was also work that was done at Northrop Grumman where I was for silicon carbide, and that has led to some military products that I was supporting. So I guess I'm very in the good position that over the years, you work on something, it's R&D, you try to make it work, you try to make it commercially viable, and then you kind of see it actually happen and grow. So I have several patents. A lot of them were in the edge termination. The edge termination is a very important thing. You can have a nice thick layer that, for example, supports 1200 volts, but if you don't have the right edge termination, you're going to break down at 400 volts, right at the edges of the device. So I did a lot of work trying to do an edge termination that's fabrication less intensive, meaning that I combined the doping for the edge termination with dopings that happened to the device itself. So it was very valuable because anything you do in the fab, and particularly in silicon carbide, where implantation is a very labor-intensive process. It's a heated implantation. So if you can combine your edge termination with other implantations in the device, so I ended up building a device where a simple implant would take care of the gates, and it would also take care of the edge termination. And the edge termination, is a very small extent. That's big, and it ended up, leading to 96% efficiency, meaning that we were getting 96% of the ideal breakdown voltage, that was of that, thickness and doping of the layer. So that's part of the work. But one that I like very, very much is one that combines optics, optical signals with electronics. And that's for a circuit breaker where you put two JFETs back to back. And one JFET, of course, is going to be conducting in the normal direction, but the second JFET is conducting in the reverse direction. So what happens there, if you exceed a certain voltage in case of a fault, the reverse conducting JFET has a PN junction, the reverse, the reverse conducting PN junction turned on. The minute that happens, you're going to see a nice purple bluish light. And the pattern is, you operate a circuit breaker, and under normal operating conditions, there's no light. The minute something goes wrong, instead of trying to detect an increase in current where you might have interference and other types of issues, you really detect the emission of a blue light that happens at the PN junction. Only when there is a fault, the PN junction gets turned on. So it's kind of a cool, neat way to combine my old expertise with optical semiconductors and playing around with light with electronics.
Nice one. So silicon carbide. So you wrote the foreword and one chapter for our silicon carbide book. So you wrote in general a lot in terms of technical articles and books. So also you will give us the next opening of PowerUp 2022. So jumping from silicon to silicon carbide, so which is the road that we need to path efficiently. I mean, also in a vision in terms of the future with the next application in mobility, energy. So energy demand is changing. So it's important also, I mean, as you said earlier, so to guarantee a good future for the next generation.
Yes, so when you come up with a new material, new technology, and of course silicon carbide and GaN are commercialized today. There's a lot more work that needs to be done. Vertical GaN is pretty much starting now, no commercial products. If you look at silicon carbide, it was recently announced 3.3 kV devices by a major company, Microchip. So that's a big development. But of course, there's the 6.5, the 10 kV, all these applications for fast charging stations, all these applications for the microgrid that will utilize high voltage devices, transmission. So there's a huge amount of work that can take place in silicon carbide, and a lot of the high voltage stuff that we need for these applications has fallen behind because people are the companies have obviously a limited number of resources, and they're putting all their resources to the electric vehicle market, which is massive. The design wins there because that's going to bring revenue in the very short term. But looking beyond silicon carbide, there are other materials whose properties are even more compelling, and these are the ultra wide bandgap material. Diamond, gallium oxide, aluminum nitride are some of them, and people are looking into those as well. And I'm part of some of this, advising some of these groups. And the most important thing, of course, is you got to have a starting material. You got to have a wafer that's relatively defect-free, in order to make large devices, and planar enough in order to pass through a silicon fab. And at the same time, you want to make sure that it can be produced at a reasonably low cost, right? Silicon wafers are very cheap, and you're competing with that. Second step is the fabrication. Okay, there's this massive silicon infrastructure and mature processes, excellent know-how, excellent reliability and yields. So the question is, how much of that can you exploit? How much of that can you leverage? And what is it that you need to do that is new? Okay, so for silicon carbide, we all know at this point very well what is available from the silicon world that somebody who does silicon understands and can do directly. And we also understand the processes that are specific to silicon carbide, don't exist in silicon. And we've built those, and we've done that quite efficiently. So the fabrication of silicon carbide is at a good point. But for a company that does silicon and sees opportunity in silicon carbide and wants to increase its volume, it wants to move its business and exploit that, the silicon carbide area as well. There's some new processes that need to be developed, and some new tools. Now, the fortunate thing is that you can take what's called a mature fab, meaning not the latest and greatest, this 2 nanometer, 3 nanometer, multi-billion expensive equipment type of lab, but an older 20-year-old lab with deep UV or even eye-line photolithography, and you can use all that equipment. And if you just buy some new equipment for the silicon carbide specific processes, you're ready to run. And that, in terms of equipment, I haven't looked at prices lately, and I know everything has been increasing in cost, but maybe 20 million will get you those tools to get started. And there's a lot of, like the implantation, which is the heavy duty new item in silicon carbide. You can outsource that. There's several companies that will do that until you're ready to buy these expensive tools or more expensive tools and put them in your fab. So there's a lot of opportunity for silicon fabs to start processing silicon carbide, and that's a great thing because it would have been a barrier if a silicon fab had to make a major modification to do silicon carbide. So when I talk to people who are going into the new world, the new frontier of gallium oxide and aluminum nitride and diamond, I tell them that, hey, you got to make sure if you want to be successful, apart from the starting wafer, the substrate that has to be affordable, large area, low defect, and planar, when you get to the fabrication stage, you want to make sure that you're exploiting silicon and you only have a limited number of processes that will require new tools, specific tools, and specific development of processing if you want to be successful.
Great. So just come back in PowerAmerica that you mentioned earlier. So I was reading a news in terms of collaboration between PowerAmerica and Navitas, I guess. I think that PowerAmerica is going to have a lot of collaboration in terms of industry companies, but also university. So this will be the goal in the future from PowerAmerica perspective.
Yes, that's correct. So what I try to do with PowerAmerica is obviously accelerate the commercialization of silicon carbide and GaN power electronics, and we get together with our members and identify barriers. What are some of the things that are holding the large scale commercialization back? And a lot of that, Mauricio, you might be surprised. It's more pre-competitive stuff, right? And it's a lot cheaper for all of us to pull our resources together and run those things and get some results and understand certain things. And then every company can take those outcomes and exploit them in a way that's compatible with their business model and the markets they go after. So I think a big benefit of being part of PowerAmerica is that the majority of your membership funds go into these common projects that members themselves select. They select the project, they select the university typically that will run the project, and then they have access to all the IP or the know-how that comes out of that project. They get the answers, and it's a lot cheaper, number one, but from doing all that work yourself. But number two, at a time when there's this massive growth and the people who are familiar with silicon carbide are limited, it's a good use if companies get together and some of the things that are holding the whole sector back and can benefit everybody can be worked out at low cost and without, as a VP, taking major resources from your teams to do that. So that's part of the benefit. And as far as PowerAmerica is concerned, any other entity, university, company that's passionate about wide bandgap and wants to see the commercialization and wants to see the benefits of energy efficiency with respect to like a cleaner planet, environmental benefits is a friend of ours, and we're very happy to work with them and have them as part of the PowerAmerica network. And that goes for companies from around the world. Everybody is welcome.
So Victor, next weekend is coming. So your next project, next holidays, next readings. So what do you prefer? Which books you prefer? Maybe with a good drink.
Yeah. So really, I'm looking at some of the classical works of Greece. Unfortunately, I'm not in a position to read them in the ancient Greek form. That's something that I'll have to work on when I get closer to retirement. It takes a little effort. So I like the Peloponnesian Wars and Herodotus, the history, Aristotle. Some of those writings are of great interest to me. I also like some of the the Russian classical, so to speak, writers like Tolstoy and Dostoevsky. Those are great books. But I guess I'm very guilty because I spend most of my time reading up and trying to learn more about silicon carbide and GaN, to the point that I take articles when I go to the beach, or so that has been occupying a lot of my time. So so this weekend, a little reading. I like to do things with my hands, so there's some things in the car that I would like to fix. So I'm going to lift it up, basically go underneath and start playing around, making some little things that need to be done, and try to get a little exercise. It's always a good idea to keep your body active and keep the blood flowing to your brain. Without enough blood in the brain, I'm going to forget everything I learned about silicon carbide, and that would be a shame. So, because that would mean I have to start over again. So, sound mind in a sound body, right? Trying to find, like everybody else, trying to find a balance between work and family, and some much needed, relaxation. So that's the goal for the weekend.
Wonderful. So, Victor, thanks a lot for having you. So, it's a pleasure to talk with you. So, thanks
Absolutely.
thanks a lot. Thank you very much.
Thank you for the interview. You take care. Have a good
Stay
afternoon.
tuned.
Bye-bye.
Bye.
Bye-bye.
Thank you. Bye.